Please take a minute or two and do the 3 warm-up problems at the top. Answers will be shown shortly. Here are the answers to the first two. So the first one ends up being natural log of x squared y cubed over z, and the second one ends up being 8 after you do a little bit of simplifying. Now in number 3, what we're going to talk about is what actually happens when you take the limit as h approaches 0 of e to the h minus 1 over h, and that becomes important as we move along. So let's do a little Desmos action. So what I'm going to do is I'm going to take this r and make it equal to e. So I basically have e to the x minus 1 over x. I'm pretending like that's an h, and what I want to do is I want to see what happens as we approach 0. So if I'm looking at this as we approach 0, it looks like it is approaching 1. When we explore this graphically, what we find is that it is really, really, really close to 1. Of course, it's undefined at 0, but we get something that is practically 1, and that's what happens with the limit as h approaches 0 of e to the h minus 1 over h. We get 1. So that becomes important as we move along. Now what we're going to do is take the limit definition of the derivative to evaluate e to the x. Now obviously you're not expected to do limit definitions a lot anymore. You have to know what they look like because on multiple choice problems on the AP test, they do it all the time. And just know that it ends up being the derivative of something. But what we're going to do is we're going to use the limit definition, and we're going to do that for a particular reason. So the limit as h approaches 0 of e to the x plus h minus e to the x all over h, because remember the limit definition is limit as h approaches 0 of f of x plus h minus f of x over h. So now we're going to do a little bit of exponential function rules, and e to the x plus h is the same thing as e to the x times e to the h. And then we'll do a little bit of simplifying here. So this is equal to the limit as h approaches 0. I will factor out an e to the x. So I have e to the x times e to the h minus 1 over h. So now let's take a look at what actually happens here. The limit as h approaches 0 of e to the x, well, that just stays e to the x. The limit as h approaches 0 of this thing, we just found out through some graphical exploration that that is equal to 1. There's a lot heavier math that we can do in order to show that, but for the scope of this course, we can just explore and see that that's 1. So what we found is that the derivative of e to the x is e to the x. E to the x, one way that it can be defined is it can be defined as the function that has its own derivative is the function itself. So that's one way that we can define it. For the second problem, I skipped a lot of the algebra with the limit definition, and we end up with e to the 2x times e to the 2h minus 1 over h. If you want to actually do the limit definition and do the factoring, you'll see that that happens. So what we can see is we definitely have an e to the 2x in our answer for this derivative. The question is, what does this thing in the green box actually mean? And so we're going to take the limit as h approaches 0 of the same thing that we had up here, except there's a 2h instead of just an h. So let's analyze this. And if I replace that e with an e squared, and I appear to find out what the numbers are approaching, it appears the number is approaching 2 as we go towards 0. So that thing in the green box basically becomes a 2. And so what it appears that we're finding is that when we take the derivative of e to the x, we have to take the derivative of whatever's in the numerator or in the exponent. And that kind of looks like the chain rule, which is exactly what we would think it is. So the derivative with respect to x of e to the u is actually e to the u, but then we also have to have this derivative that we're taking with respect to x of whatever that other function u is. So that's basically a chain rule application. Now we're going to find the derivative with respect to x of a to the x for a is greater than 0 and a is not equal to 1. So real quick, we'll do another limit definition of this. So this ends up being a to the x plus h minus a to the x all over h with the limit as h approaches 0. We get the exact same algebra that we had with the e. So limit as h approaches 0 of a to the x times a to the h minus 1 all over h. And now our job is to figure out what goes on there. So this is kind of why I set up the Desmos the way I did, where I have this r, because now instead of having r be e squared or something, now what I can do is kind of make it a slider. So if r is equal to 1, clearly 1 minus 1 is 0, and that really doesn't do any good. It's always 0. But if I change this, this function up here continually gets higher and higher and higher. So that represents our a, whatever a is in our problem. And so let's just stop at 17, for example. As I approach 0, what I'm noticing is that my y value appears to be getting really close to whatever the natural log of that number is. So notice it appears to be kind of sandwiched around that 2.83 number. If I make it kind of small, like r equals 4, notice that it's getting sandwiched around 1.38. So what I'm noticing is that whatever number is here, what happens is the natural log of that number is basically what happens as the limit of this approaches 0. So when I do this, the limit as h approaches 0, a to the x is not dependent. That consistently stays the same when I take the derivative. But then I have this other thing that's going on, and what happens is I always get the natural log of whatever my number a is. Okay, natural log of a times a to the x. Oftentimes we write it in the other order. So we have a to the x times the natural log of a. And if we go back and look at the previous problem, what is the natural log of e squared? It is 2. So that makes sense that that would go here. What is the natural log of e? It is 1. So it makes sense that this appears to be a generalization of what's going on. So if we look at this last problem, the derivative with respect to x of a to the 3x squared, what we end up with is a to the 3x squared times the natural log of a, and then we have a chain rule component. So this 3x squared, we have to take the derivative of that, so we get 6x. So the derivative of this would be 6x times a to the 3x squared times the natural log of a. So if we have some function that isn't x up here, then what we have to do is make sure that we take the derivative, which is a to the u times the natural log of a, and then we still have to have that chain rule component, so we're going to multiply it by du dx. One more thing, I don't know if your worksheet has a 5 in there, but that would be the answer if the worksheet had a 5. Now let's talk about the derivative of the natural log of x. We know that this is 1 over x because we were told this at the beginning of the unit, but what we kind of want to do is figure out why that is. So we can use the fact that we now know inverse function derivatives, and since e to the x and natural log of x are inverse functions, if we say that f of x equals e to the x and g of x equals the natural log of x, we know that these are inverses. So if we want the derivative of the natural log of x, which we're calling g of x, this is going to be equivalent to 1 over f prime of g of x, because that's our rule for inverse function derivatives. So g of x is natural log of x, and the derivative of f of x is e to the x. So we can say e to the g of x, which is natural log of x, this is 1 over x. And so that's something that we can kind of show why that works. Now, if we take the derivative of the next problem, which is 1/3 natural log of x, we get 1 over 3x. So the derivative of the natural log of u, this actually doesn't really apply to what the problem we just did, but the derivative of the natural log of u is 1 over u times du dx. We have that chain rule component. Now, once again, that's not like this problem necessarily, so let's find a problem that it is like. So for example, take the derivative of the natural log of 3x. So if we take the derivative of the natural log of 3x, it's 1 over whatever was on the inside, so that's our u, times du dx, which is 3. So ironically, the derivative of the natural log of x is actually exactly the same as the derivative of the natural log of 3x. Okay, finally, if we have the derivative of log base a of x, we can use the same inverse function rule, and we end up getting 1 over x times natural log of a. You can do that on your own if you want, but this ends up being the rule. If we had another function u in there, we end up with 1 over x times the natural log of a times the chain rule component, du dx. And we'll show that in this particular problem. So natural or log base a of x squared minus 7x becomes 1 over x squared minus 7x times the derivative of the inside. So I guess we don't really need to put the 1 up there. So we have 2x minus 7. And then, so that's the chain rule component. And then we have this natural log of a that has to be in the denominator. So to summarize, this is kind of what we learned here for these derivatives. One thing I want to do is I want to show you, if you forget how to do something, what to do. So these should clearly be memorized. You should definitely memorize the 2 things that I just circled. And if you don't remember where the natural log goes in a case where you have a non-e or non-natural log type situation, so if you have one of these situations over here, for example, let's say we have y equals 4 to the x, and we want to take the derivative of this, and we don't remember what to do. One thing that's pretty easy to do is to take the natural log of both sides. Notice that the natural log of 4 to the x is the same thing as x times the natural log of 4. Now we can take the derivative of this implicitly, so we have 1 over y dy dx equals the derivative of x is 1, and natural log of 4 is a constant, so we can just leave that as natural log of 4. Then we multiply the y over to the other side, so dy dx equals y times the natural log of 4. And what was y originally? It's 4 to the x. So 4 to the x, natural log of 4. Notice that this process gives you what you should expect to get. So if you can memorize this, great. If you forget, you can derive it pretty easily using implicit differentiation. Secondly, let's talk about how I would do the other one if I forget. So let's say I forget the rule for this one down here. What I would do is I would change log base a of x by the change of base rule for exponents. So if I have, let's say, y equals log base 7 of x, I could rewrite this as natural log of x over natural log of 7. And that makes it way easier in order to do everything, because then if you take the derivative, dy dx, the derivative of natural log of x is 1 over x. And natural log of 7 is a constant, so I don't have to do the quotient rule or anything like that. So I would end up with x times the natural log of 7 in the denominator, which matches up perfectly with what that rule is. And clearly, if there are things other than x in there, we would have to do a chain rule and stuff like that. But those are just quick ways, if you forget what the rules are, how to derive them. So real quick, I want you to do some practice, and then I will put some answers up. Here are the answers to the first four. Note that in letter B, when you do the chain rule and you have that times 2, you cannot multiply that to the 4 to the 2x. So you cannot make it equal to 8 to the 2x times natural log of 4. Okay, now E and F, I kind of want to do with you because these require a little bit of trickery, so to speak. So if we want to find dy dx when y equals x to the x, if we have a variable in the base and a variable in the exponent, that becomes a lot trickier. So the trick is, back when a couple of problems ago, when we were doing this one, and we found the trick to remembering if we forgot was to do a natural log of both sides of the equation. That's something that actually becomes a highly valuable way in order to get some derivatives. So I'm going to take the natural log of both sides of this equation. If I end up doing this, I then get natural log of y equals x times the natural log of x. And the reason why I can do that is because a variable in the exponent or anything in the exponent can move down when I have a natural log. Now I can implicitly take the derivative. So 1 over y dy dx equals product rule over here. So derivative of x is 1 times natural log of x plus x times the derivative of natural log of x, which is 1 over x. That ends up being 1. So when I simplify this, I get dy dx equals y times natural log of x plus 1. I will have to replace the y with what y originally was. So that's x to the x times natural log of x plus 1. Similarly, over here in problem F, if I have dy dx of this is kind of a nightmare. You can end up doing it, but there's a lot of work involved. If I take a natural log of both sides of this equation, what I end up with is I had this this thing over here, which is kind of nasty. So I have the natural log of x plus 7 to the 2/5, or x plus 7 squared over x, and then that's to the 1/5 power. So with this natural log, I can do some expanding and condensing. So I get 1/5 times the natural log of x plus 7 squared minus 1/5 times the natural log of x. I can move that 2 down, and it can become 2/5 natural log of x plus 7 minus 1/5 natural log of x. Now let's take a derivative. So if I take the derivative of natural log of y, I get 1 over y. Sorry, I'm going to draw a line to make sure that it's distinguished. 1 over y dy dx equals 2/5 times the natural log of x plus 7. If we take the derivative of that, I get 2 over 5 times x plus 7. The derivative of the inside is just 1, so that ends up not being that hard, minus 1 over 5x. And then I have to multiply the 5, the y over, so I get, sorry, I don't know why I said 5. So dy dx equals y, which, if we remember correctly, was that nonsense. So that's the 5th root of x plus 7 squared over x times 2 over 5 times x plus 7 minus 1 over 5x. And that would be my answer there. At the bottom of the page, if we have one of these nasty situations, we want to use this thing that we just learned called logarithmic differentiation, where you take, I would use the natural log to avoid the nasty natural log of a in the denominator. Natural log of y equals natural log of whatever the junk is over here, In these two problems, we just had some good examples of what the junk is, and then we will get 1 over y dy dx equals, and then we're going to take the derivative of whatever's over here, multiply the y over, and it ends up working out pretty well.